Okay. So for the second question, it asks, what is the moment of inertia? What is the moment of inertia for a rod of mass m and length L? I'm just going to erase that so that. Okay. What is the moment of inertia for a rod of mass m and length L? Okay, so there's a few different ways that we could represent this. So start off, moment of inertia is either sum over mass times r squared, and that's for discrete points. Actually, I'm going to just do that because I realized, so I want to start over. So moment of inertia is for discrete points, sum over the discrete masses times the distance of the masses from our moment squared. Or for a continuous object, which this is, it's the integral of r squared dm. So if we set it up now as we're going to put our moment here, and I'm just going to call that y. And I'm going to put my rod extending down this way. And so then the rod is length L. And its total mass is m. And I'm representing the rod as essentially a one-dimensional object. So it just goes in one line. But our mass is m, but I'm going to call it sigma L, where sigma is our mass density, and this is a length density since it's a one-dimensional object, and so the total mass is just the density times the length, or our sigma is mass over length. But if we consider an infinitesimal mass at some d x, then the dm will just be sigma dx, right? Because that's our conversion factor between a small length dx and a small mass dm. And I guess in this case, actually, I should change it to an r, since that is our r, and I'm going to actually call it a dr, and I'm going to call this a dr, just so that I don't have to change units from what I called there. So that would be our r, that would be our dr, and that's our dm. So that means that for this problem, our moment of inertia is integral r squared sigma dr, bringing the sigma out front, and our integral is going to go from, the way I've drawn it is from 0 to minus L, or from minus L to 0. So I'll keep it that way. And sigma, so the integral of r squared, you bring the power up to 3 and then divide by the power. So that would be r cubed over 3 from minus L to 0, which is sigma. So when r is 0, the whole thing's going to be 0, and then we're going to subtract the minus L cubed over 3. The negative signs will cancel, and it'll be sigma L cubed over 3. Giving myself a little more space. So our total mass, so our moment of inertia is now this sigma L cubed over 3. Our total mass is sigma L, so we can put that in, and we'll get 1/3 mL squared. Okay, and so that's our moment of inertia rotating about a a moment which is at one end of the rod, and the rod's perpendicular to the axis. We could also do it where the moment on the rod is right through the center, and so then that's L over 2, and that's L over 2. And the problem is fairly similar, so again, we would do integral r squared dm. dm would still be sigma dr. So then this would be integral r squared sigma r squared dr. But now the integration limit would be minus L over 2 to L over 2. Again, this integral is just r cubed over 3. So it's just sigma r cubed over 3 between minus L over 2 and L over 2, which is sigma over 3. I'll just pull the 3 out. L over 2 cubed minus a minus L over 2 cubed. So that's going to give us L cubed over 2 cubed, which is 8. So sigma over 3 times L cubed over 8. The minus and minus will cancel, so make it plus L cubed over 8. So L cubed over 8 plus L cubed over 8 is 2. L cubed over 8. Which is then canceling the 2 and turning this to a 4. This is then sigma over 3, L cubed over 4, multiplying those through, sigma L cubed over 12, and then using again our mass relation, we can make that substitution, and so it's just ml squared over 12. So then the moment of inertia in this case, where the rod is rotating about a central moment, is ml squared over 12. So then showing everything for everything I did. We can look at the solution here. So the solution given runs through a few different cases, actually a couple extra cases more than I did. So passing through the midpoint, we get ml squared over 12. If it's perpendicular to one end, we get ml squared over 3. But the solution here also just gives the answers for if they're if it's inclined at an angle, which might be quite simple, but I'm not sure. But these just give the direct results for these values. But I'm not going to run through all of those right now. But this solution is correct. It just doesn't run through the exact the mathematical structure.